Hi, everybody. Thank you, Renata, for the introduction. So today I'm going to present a joint work with Professor Justin Rohrer and Professor Robert Beverly and Naval Postgraduate School, and our team at Sorbonne University with my two advisors, Olivier, Fourmaux, and Timur, Friedman. So there are millions of diamonds out there in the internet, and we are not seeing them. I'm going to show you today a system, Diamond Miner, that allows you to see these diamonds. By diamond, I mean the shape formed because of the presence of load balancing routers in the internet. So why is it important to capture these diamonds? Because nowadays IP load balancing is prevalent. It improves the capacity and the redundancy of internet path. And existing techniques do not accurately capture load balanced path at internet scale. And this gives us a bad idea of the true resilience and the structure of the internet. And to give you an order of magnitude, Diamond Miner revealed 64% more links than existing internet maps. So why can't we see these diamonds? Because in order to map these diamonds today, we have basically two options. Either use single path techniques, such as traceroute, or use the multipath technique with NSDI Paris traceroute. And both of these techniques cannot completely capture the diamonds at internet scale. So let's see first the limitations. So we will work with this toy example all along the presentation, and the goal will be to discover this topology. We do not know this topology in advance, so let me introduce the notations. So VP is our vantage point. The /24 is a destination prefix, and the letters are IP interfaces. And A is an upper destination load balancing router that is balancing the traffic over two paths, through B and through E, and E is also an upper destination load balancing router that is balancing the traffic over F and G. So the single pass probing technique discovered diamonds inadvertently. Let me explain. If you fix a destination in the /24 destination prefix, and you send one probe per TTL, which is basically how traceroute works, you will discover one path. And because A is a per destination load balancer, you're guaranteed that if you send probes with the same destination, they will follow the same path. And when you send a probe with a destination that you have never used before, you have no idea of which path it will take. Then if you probe to another destination in the /24, because A is a per destination load balancer, eventually you will discover another path. But the thing is that you have no statistical guarantees that you have discovered all of them. So if you want statistical guarantees, you have to use the second technique, which is the multipath technique. So it's a hop-by-hop technique that progressively achieves statistical guarantees for every node discovered. So let's see how it proceeds. So let's say we have discovered A at TTL1, and now we are trying to discover the successors of A. So if I send one probe at TTL2 with a destination in the /24, I will discover one interface. Let's assume here it's B. And if I send a second probe to hop 2 with a different destination in /24, because it's the first time I use this destination, I do not know which path it will take, and maybe I will rediscover B. And eventually, with the third destination, I will discover E. But nothing tells me that A is not a third successor. So I have to keep probing at TTL2 until I reach a low failure probability that A has only two successors. And that's the purpose of the table in the top right corner here. I have to send 11 probes to get a failure probability of 5% that A has only two successors. And once I have sent these 11 probes and have only discovered that A has two successors, I can say that the node A is resolved. And once A has been resolved, the algorithm steps to TTL2 where it tries to resolve B and E. So to resolve B and E, I must send probes that go through B and through E. And by using the destination that I used to find the successors of A, I know which path they will take. So I just take these destinations and send the probes this time at TTL3. And what I'm able to discover is the successors of B and E. And here, what I can notice is that I have enough probes to resolve B, but because E, I have discovered that E has two successors, I need more probes. I need 11 probes. So I have to find destinations that go through E first, and then I keep using these new destinations until I get 11 that go through E, and then I can mark E as resolved. The thing here to understand is that this algorithm proceeds TTL per TTL, node by node, because we want to send the minimum amount of probes to achieve the statistical guarantees. And this slows down the probing dramatically. On complex topology, it can take several minutes to resolve all of the nodes of a topology, preventing the usage of this technique at internet scale in a reasonable time. So let's finish this example. At TTL3, same thing. I try to resolve C, F, and G. So here, for example, I have enough probes to resolve C and F, but not enough to resolve G. So I send probes at TTL3 to find new destination that go through G, and then send the one that goes through G at TTL4 so that I can resolve G. And finally, I try to resolve G, and once I have resolved G, I see that all the nodes of this topology have been resolved. So what I say is that I can mark this /24 prefix as resolved. So as we've seen, both of the current techniques are not able to capture the diamonds at internet scale with statistical guarantees, because single pass probing technique offers no statistical guarantees on the discovery, and current multipath probing technique, because it resolved the nodes TTL per TTL, preventing its usage at internet scale. So as a result, systems that perform continuous surveys of internet topology mapping have turned off this multipath capacity. So the consequence of this is that we are working with incomplete internet maps. So the question is how to build a system that provides statistical guarantees at internet scale. And the answer is the contribution of today, Diamond Miner, a massively parallelized probing system to map diamonds at internet scale, providing statistical guarantees. So the key ideas behind Diamond Miner are that we will no more resolve the nodes TTL per TTL. We will resolve all of the nodes of the topology concurrently. And how do we achieve this? Is that proceeding by round. So what is a round? So the round will take as input the entire topology discovered by the previous round, and it will output the number of probes to send per TTL per destination prefix to achieve statistical guarantees. The important thing here to understand is the concurrency aspect of the new algorithm. It will be able to resolve millions of nodes in parallel, because we're not proceeding node by node TTL per TTL anymore. So again, we will reuse the same term topology that we used for the two previous techniques. So recall A is still a per destination load balancer as well as E. So first, Diamond Miner, instead of proceeding TTL per TTL, will send will send all the probes at once. So it's important to realize that all of these probes are now sent concurrently. And 6 different destinations in the /24 are sent, which correspond to the minimum number of probes to reach a failure probability of 5% that a node has only one successor. So here, we see that we have discovered all of the IP interfaces except G. And in terms of successors, we have discovered that A has 2 successors, and all of the others at the moment have only 1 successor. So this first step is called the first round of probing. Then Diamond Miner gathers the number of replies that it got from the different IP interfaces. So it got 6 from A, 4 from B, 4 from C, 6 from D, 2 from E, 2 from F, and 6 from the /24. And in order to compute where it should send the next probes, Diamond Miner answers the following question. How much probes do we need per TTL to resolve all of the nodes if there were nothing more to discover? So let's perform the computation TTL per TTL. At TTL1, we have only discovered A. And we know that A has 2 successors at the moment. So the number of probes that are needed to reach the 5% failure probability is 11. So we need 5 more at TTL1. At TTL2, the situation is a little bit more complicated because we have discovered 2 nodes. So the algorithm computes the number of nodes needed to reach the statistical guarantees for B and E. If they add only 1 successor, it is based on the number of the replies that they got. I refer you to the paper for the details of this computation. So the miner computes that we need 12 for at TTL2. And at TTL3, we have currently the same configuration as at TTL2. So we also need 12. And at TTL4, we also need 12 because we want to find the successors of the nodes found at TTL3. So we also need 12. And at TTL5, what you notice is that we already have 6 probes that go through G and through D. And D has only 1 successor, the /24. So we can mark D as resolved. So once we have computed the number of probes needed, we send those probes in the network. And this time, you can notice that G has been discovered. And let's see now which node has been resolved and which node has not. So at TTL1, what we see is that now we have 11 probes that go through A. So we can say that A has been resolved, so we don't need any more probes at TTL1. At TTL2, we see that B has been resolved because it has more than 6 and 1 successor, but E has not been resolved because it has 10 probes and 2 successors, so it needs 11. So the same type of computation that we did at round 2 brings that we need 2 probes at TTL2. At TTL3, we see that C and F have been resolved, but not G, and the computation brings 9 to be able to resolve G. TTL4, 9 as well, because it helps for resolving G. And at TTL5, we have 0, still 0, because D has already been resolved. So then we send those probes for round 3, and let's see if we still have nodes that have not been resolved. So the state of the topology is the following state. So at TTL1, we still have A and 2 successors. So A is already resolved. At TTL2, B is also resolved. And now E is resolved because we have 11 probes that go through E. And at TTL3, G is now resolved because we have 7 that go through G. And at TTL4, D is already resolved, and TTL5 as well. So far, all of the nodes for this /24 destination prefix are resolved, so we can say that this /24 has been resolved. So again, let me just bring back the key ideas of this algorithm. So we are no more resolving the nodes TTL per TTL. We are resolving the nodes, all of the nodes concurrently with a round-based approach. With the input of all of the topology discovered by the previous round, and the output, you've seen that we are computing the number of probes needed to send per TTL per destination prefix to achieve statistical guarantees. So we have shown this example of diamond miner on the /24 prefix, but actually diamond miner can perform this algorithm on all the /24s of the internet in parallel, because we are no more constrained by the hop-by-hop probing technique that we've seen in the beginning of the talk. And we will see that it enables us to decrease dramatically the time to completion. So now that you have the details of the diamond miner algorithm, I'm going to give you a couple of results. So first, some results about the system itself, and then some results compared to some state-of-the-art internet mapping systems. So we have deployed the gminer system on one machine at Sorbonne University, and we have limited ourselves to 100,000 packets per second. And the first result that I want to share with you is the miner capacity to resolve the prefixes, meaning its capacity to achieve the same level of statistical guarantees that the classic multipath approach would have. So on the x-axis of this graph, you have the number of rounds, and on the y-axis of this graph, you have the CDF of the resolved prefixes. And we show the results on 3 snapshots of the miner that have been taken during a week. So we can see that 10 rounds are enough to resolve more than 99% of the prefixes. So what we can say is that diamond miner manages to obtain the same level of statistical guarantees as the classic approach. So the second results show the trade-off between the overhead in terms of probes compared to the time of completion. And this result is pretty striking because we see that for 12% more probes, we can dramatically reduce the time to completion, going from 64 years to 2.5 days. So the 64 years estimation is based on a calculus that we've made given the most recent survey of IP load balancing that we've made in the last IMC 2018 paper over 350,000 destinations. So another aspect of the evaluation that I want to share with you is how diamond miner compares with other internet mapping systems in terms of topology discovery. So for that, we have also deployed diamond miner on 6 Planet Lab Europe's nodes at a lower rate, 10,000 packets per second. So we were not able to deploy at 100,000 packets per second because we didn't have this wasn't dedicated nodes for diamond miner. And so we have compared to 2 state-of-the-art tools in internet mapping. So the first one that we have compared with is YARP. So YARP is the first tool that brought the ideas to allow fast topology mapping. And we can say that it is a fast single-pass probing technique if I refer to the taxonomy that I've used at the beginning of the talk. And the result of this table is that we observe that in both setups with 1 and 6 vantage points, YARP discovers less nodes and links And our interpretation of this is that because YARP is a single pass probing technique, it has a multipass capacity turned off. The second system that we have compared with is ARC. So ARC is a system used by CADA at UCSD and performs internet-wide surveys from multiple vantage points, about 110 in 2020. So ARC is also using a single pass technique. It is a state-of-the-art in terms of internet-wide surveys. So a survey consists in performing single pass Paris trace route to one random destination per /24. So as we saw at the beginning of the talk, the consequence of this method is that across multiple surveys, ARC will inadvertently be capable of detecting diamonds. But also, as we saw in the beginning, it does not give any statistical guarantees on this diamond discovery. So our explanation on the results of this table is that the number of links that diamond miner is capable to discover is the 64% more because of the prevalence of the load balanced path in the internet. And our explanation for ARC being able still to see more nodes is that just because it has more vantage points, so the nodes close to their vantage points, diamond miner might be unable to see them. So to conclude my talk, I would say that Diamond Miner is the first system capable of tracing diamonds at internet scale with statistical guarantees. And it can obtain the most complete IP-level topology view from a single server. And all our code is publicly available at this address. So thank you for your attention, and I'm happy to take questions.
Questions?
So how this fits in, for example, each carrier, when they have an MPLS core, they hide the TTL. Sometimes they plug the TTL for security reasons.
So you mean MPLS tunnels?
Yes.
Yes, so this work is not able to discover MPLS tunnels, except the one that are visible to, like some MPLS tunnels are visible because you have the XMP extension that come back in the reply. But this work is not capable of revealing MPLS tunnels.
Okay.
Interesting talk. How do you define concurrent? You talk about 100,000 packets per second and then 10,000, but what if it were 10 packets per second or 1 packet per second? At what point is it no longer concurrent enough for your definition?
So concurrent in this work means that we're able to resolve all of the /24 in parallel, meaning that we're not constrained anymore by the algorithmic limitation of the hop-by-hop probing, because in the hop-by-hop probing technique, you have to wait for replies, updating the state of the node that you already have seen, and that's what concurrent means in that work.
In your statistical inference, do you assume equal cost multipath?
Yes. So that's one of the hypotheses of the MDA algorithm. That is, it is evenly distributed in real world. For example, on Cisco, it's so in the from the documentation we have seen that it might not be that evenly balanced. However, in the majority of the cases, what we've observed is that it tends to try to be uniform across the path. But yes, this work also. So we will be able to discover uneven distributed load balanced path, but the statistical inferences do not take into account this case.
Yes, I mean, I was wondering, how do you guarantee that the statistical inference is correct if you don't know the weights?
Yeah.
So that, okay, thanks.
So the question is around, like you mentioned, we do traceroute kind of a thing where ICMP response come, and from there we validate, figure out that probe is completed or not. So in some of the routers, they have restrictions that they don't respond the ICMP. So in that case, how do you take care of figuring out if the probe completed or is it incomplete kind of thing?
So if the router shuts down the ICMP, we're not able to get any information from it. So
any data you found that how many percentage of the routers in the public didn't respond for it? Because without that we cannot complete the whole probe, right?
No, I don't have any precise figure here.
Okay, probably we can talk offline.
Yeah,
more
sure.
details. Thank you.
Thank you very much. Let's thank Kevin again.